Of the four fundamental forces, gravity is the most familiar, seemingly unchanging, ubiquitous, and maybe even a little boring. We first meet gravity while dropping our first toys, and later get to know it from the thrill of a roller coaster and the scabs on our knees. As the years go by, it keeps our feet on the floor and our butts at our desks. But gravity is far more dynamic than modest everyday interactions suggest. Over the planet, its attraction varies between 32.09 and 32.25 feet per second squared. In these tiny fluctuations, scientists have found, is a wealth of information about our planet's structure, as long as they can measure the signals. And now they are developing the most precise gravity sensors ever made, by wielding the rules of quantum mechanics. Physicist Babak Saif, who works at NASA's Goddard Space Flight Center, in Maryland, has built an instrument that uses atoms to sense gravity. Since an object's gravitational attraction is directly related to how massive it is, this device essentially weighs nearby material. The instrument is so sensitive that while they were testing it, it yielded different gravity measurements before and after the scientists broke for lunch, says Saif. It was detecting the food in our stomachs, he says. The quantum sensor, which NASA has developed with Bay Area-based company Aosynth, relies on some 100 million cesium atoms. The device launches the atoms inside a cylindrical column and times how quickly they fall. As dictated by quantum mechanics, the atoms behave both like particles and waves. Imagine them sloshing in the column like water waves. As an atom wave ripples up the column and back down, it overlaps with itself to create an interference pattern of crests and troughs. That pattern varies based on how fast the atoms rise and fall and can reveal tiny fluctuations in gravity. Researchers want to launch a version of this machine into space to map Earth's gravitational field, says NASA Goddard geophysicist Scott Luthker. In particular, you can use gravity to monitor the masses of glaciers, detect changes in aquifer levels, and even observe how water and air move in a tsunami. This gravity sensor would replace a pair of satellites currently orbiting Earth known as GRACE-4. Over a month of measurements, the quantum sensor can detect a 1.5 centimeter change in sea level over an area the size of Hawaii's Big Island, says Luthker. Compared to the current satellite pair, it can map Earth's gravity 10 times more precisely at 4 times the spatial resolution. Its high precision derives from a design that isolates the atoms from all forces except gravity, in part by keeping the particles in vacuum near absolute zero. Other researchers want to use similar sensors for projects closer to Earth's surface. At the University of Birmingham, in the UK, researchers have built a prototype gravity sensor, also based on atom interferometry, for planning infrastructure projects. Before civil engineers can start construction, they need to check that their blueprints do not interfere with buried sewage pipes, building basements, or hidden mine shafts, for example. Gravity sensors can detect underground structures 10 to 50 feet underground without drilling expensive boreholes, says Nicole Metier, a civil engineer at the University of Birmingham. While commercial gravity sensors are already available, civil engineers don't widely use them because measurements take a long time, and the instruments frequently need to be recalibrated. The quantum sensor shouldn't have these issues, says Metier. Metier and her colleagues think that the quantum sensor could help the construction of a planned high-speed rail in the UK known as HS2. Part of the HS2 railway, which connects the cities of Birmingham and Manchester, will snake through the so-called Black Country, a region known for its Industrial Revolution-era coal mines. There are probably hundreds or thousands of mine shafts, says Phi.